We want to graph y equals log base 3 of x. Okay, now the easiest way I can tell you is because if you go up there and you're like, okay, I'm going to pick my x's. Let's say I pick my x's to be -2, or let's say even +2. Well, how are you going to solve log base 3 of 2? I don't know what log of 2 is, especially if I don't even want to use a calculator. Let's say we didn't have one, couldn't use it. How on earth am I going to graph this? Okay, and this is the way I'm going to show you, and this is how the easiest way to graph all logs. So if you want to ask me, hey, are we going to do this every single time? Yes, do this every single time. Take it out of log form, put it into exponential form. Okay, so this says start with your base. Our base is 3. That rule says go across the equal sign to get your exponent, and then come back to set it what you're going to set it equal to. So this is the exact same thing as that right there. 3 to the y equals x. And now this time, instead of picking my x's, I'm going to pick my y's, and then I'm going to plug in and then find my x's that way. And yes, do this every single time. When you want to graph a log, do this. Take it out of log form into exponential form and pick your y's. Okay? So this is saying basically 3 to the 0, which is anything to the 0 power is 1. 3 to the first, which is 3. 3 squared, which is 9. Okay? 3 to the -1, change that exponent to positive, and take the reciprocal of the base. So 1/3 to the first. 3 to the -2, make that exponent positive, take the reciprocal of your base. So 1/3 squared, when you come up here, is 1/9. Okay, now, granted, it's going to be a little weird graphing this from this kind of T-chart, but definitely something we can do. So let's see here. Our x values, let's go 1, 2, 3, and I'm going to jump way out here. We're going to make that 9. And 1, 2. Okay. So this is saying that when I just go over to a 9th, I'm down at -2. Really, really, really close to that y-axis. When I go over to a 3rd, I'm down at -1. Over at 1 to 0, 3, 1, and finally way over at 9, I'll get up at 2. So a log is a very slow rising curve, and it kind of goes like that. And then just like we did for the exponential function, I want to make sure I put in there my asymptote, and that is a vertical line, so it's x equals and then 0. Okay, let's go to example 3. We're going to simplify using our properties of exponents. So looking at all those, and let's talk through them. Okay, this is just kind of getting a grasp back on our rules of exponents. So I've got two things, everything's multiplied together here. I've got a base that's raised to a power, and then it's times another thing. So first of all, let's take care of this first one because we got this upper power sitting here. So if I square everything in there, 2 squared is 4. And remember, one thing raised and re-raised, we're going to multiply those exponents. So that makes it x to the -6 times -4, x to the 5th. Okay. And then now multiplying, since it's all, we really don't need the parentheses, I could just put 4 times x is to the -6 times -4. It's all multiplied together. So it's going to be -16 x to the -1. And if I want to write this with positive exponents, the -16 is just a negative number. It doesn't have anything to do with like having a negative exponent. So it would be just -16 over x to the first. All right, let's go to the next one. 4 and 12, we can reduce those because 4 goes into 12 3 times. And then from here I can do one of two things. If I can just make the exponents positive and then reduce that way if I want to. Well, the 3 stuck where it is because it has a power of 1, so it's just going to stay there. The b to the -4 is negative, so I'm going to bring that down to make it positive. And the b to the -6 is going to come up. Okay, so let me reiterate the fact that down here it's 3 times b to the -6. So when I move this b to the -6, 3 doesn't go with it. It's by itself. Okay? And then just cleaning it up, obviously the 4 down there are going to cancel with the 4 of them in there, leaving just 2. So our answer is b squared over 3. All right, let's go to the next one. Up here in the top, anything to the 0 power is always 1. And then down here in the bottom, it looks like we've got 3 individual things, all of them being re-raised. They each have their power as is, and then we are re-raising them. So we're going to multiply that outside power in. Not going to multiply it to bases at all. It always multiplies just to powers. So it's 2 to the negative 6, x to the negative 6, and y to the 4th. Always with an outside power, you just multiply it into the existing powers. And now, if they have negative exponents, we're going to move them up. Remember, again, we have individual pieces, so we treat them individually. The y to the 4th is good, so we're going to leave that in the denominator. We're going to move the 2 to the now 6th up, and then x to the 6th up. And that's great as far as if you want to go ahead and find 2 to the 6th, it's fine if you want to. If not, this is perfectly great, and you can leave it just right here. Okay, let's go on to example 4. I want to solve an equation where I have basically an exponential function equal to an exponential function. Okay? And we have this great rule, this really, really cool rule that says if these two bases equal each other, if we can get the two bases to be the same, then the exponents have to be the same, right? Because the only thing that 10 cubed can equal is 10 cubed. So if the bases are the same, then the exponents have to be the same. Okay, over here they are. So right now we can go, all right, 2x minus 1 has to equal x plus 3. And solving this out, let's move that x over. Let's move that negative 1 over. So when I subtract x, 2x minus x, 3 plus 1 will give you x is equal to 4. Let's check our answers. If I plug in 4, you'll get 10 to the 8 minus 1, so 10 to the 7th. And 4 plus 3 is 7, so 10 to the 7 equals 10 to the 7th. Awesome. Okay, example 5. Now we have to do a little more work here because my bases aren't as obvious anymore. One's an 8, and another one's a 32. Okay, well we got to think. What power or what multiple do they have in common? You know, 8 is like 4 times 2, but we don't really want it as a factor. We don't want to factor these. We want to think of them as powers. Okay, so we can think of is the fact that 8 really is 2 cubed. Okay, let's go to 32. 32, so that would be 2, 4, 8, 16, 32. That is 2 to the 5th. Ah, look, they both have a common, they have a power in common. They're both powers of 2. Now we just got to go about rewriting this though. Okay. First of all, let's focus on this right side. So I'm going to leave just 8 to the x as is. I want to flip this. I don't want to look at a fraction anymore. I want to keep it a whole number. So we have that rule that if I want to flip the base, then what that means is I need to make my exponent negative. Okay, and notice how I'm putting the exponent in parentheses because I want to make all of this exponent negative. Okay, that's the same thing I told you guys when we were graphing. If I said graph 2 to the negative 2, we can make that exponent positive and take the reciprocal of the base, right? Well, we're doing the same thing. Let's take the reciprocal of the base and then just switch the sign of your exponent. We're doing the exact same thing here. Okay? All right. So that helps just a little bit. Let's go through another step. Where all I'm going to do is distribute that negative up there. So just negative x plus 2. Okay. Now, from here, let's just focus on these bases. Okay. I can write 8, like I said, 8 is 2 cubed. So I can write that as 2 cubed, all of that to the x power. So instead of writing 8 to the x, I just converted 8 as 2 cubed. Still the same thing though. And with 32, I can take what I have, which is 2 to the 5th, all of that to that x plus 2. Okay, so again, all I did is just rewrite these bases as powers of 2, and then anytime you have one base that's raised and re-raised, we multiply those. So 2 to the 3x is equal to 2 to the 5 times negative x plus 2. All right, now I've got that cool property. The bases are equal, now the exponents have to be equal. So 3x has to equal, I'll go ahead and multiply here, negative 5x plus 10. Make sure I distribute there. Okay, let's finish solving this out. Let's move that negative 5x over. So 8x is equal to 10. Divide by 8, and x is equal to 5/4. Box that sucker up, and we are done. Let's go on to the next problem. Okay. Alright, if f of x is equal to ax e to the negative kx, we want to find f of 3 if we know f of 1 equals 5 and f of 2 equals 7. Okay, so with this problem, they're giving us basically two pieces of information. Remember, anytime you have a number inside of here, that's your x, and then right here, that's an x value as well. So we've got two conditions going on here. One, okay, where my function's going to equal 5, so I have 5 is equal to when when x is 1, so a times 1, just kind of plugging 1 in right here. There'll be a e to the negative k, because a is going to be, or all my x's are going to be 1. And then I have a second one. The second one says, okay, my function is going to equal 7 when my x value is 2. So a times 2, I'm going to write that kind of as 2a, e to the negative, and I'll write that as 2k. Okay? So those are the two conditions using that information they've given to us. And so what I've got to do is got two variables. I've got an a and a k that I've got to figure out. And I've got two equations to help me do it. What I've decided to think about is let's divide both sides here by a. Okay, so in other words, 5 over a is equal to e to the negative k. All right, so in other words, if I see an e to the negative k, I can replace it with 5 over a. Let's go to this equation over here on the right. Let me pull off the 2 off the front. Let's divide that off. So it says 7/2 is equal to ae to the negative 2k. I can replace an e to the negative k with this, and I have an e to the negative 2k. So, what can I do? Let's use our rules of exponents. I have 7/2 equals a. Can I write that as e to the negative k squared? Because if I have a base that's raised and re-raised, remember I just multiply those two together? So negative k times 2 is negative 2k. And there you go. I have an e to the k right there, so I can make my substitution. And this will say 7/2 is equal to a. My e to the k is now 5 over a, all of that squared. Okay, so further simplifying, then I have 7/2 is equal to a times 5 squared is 25. A squared is obviously a squared. All right, I've got a to the first out front, so that's going to cancel with one of those. So I'm really looking at 7/2 is equal to 25 over a. And if I do some just cross multiplying, it tells me that 50 is equal to 7a, or a is equal to 50 over 7. Okay, so I know what a is now. Let's go about finding what k is. How am I going to get k from a? And while we think about that, let me just erase some of this information so we have some room to work a little bit here. Okay. Well, if I go to the piece that they're asking us to find, we could just even write our answer in terms of k. Okay, because they want us to find f of 3, so they're giving us a value there of x value of 3. So right now, f of x is going to equal my a, which we said was 50 over 7, x, which is 3, e to the negative 3k. Okay, so if I just kind of clean this up a little bit more, f of x is 150 over 7 e to the negative 3k. And you know what, and for this problem right here, if I do anything similar to this, like if you have something similar in your homework, it'll be a lot easier the one in your homework, believe it or not, because I picked the harder one of the two. That there's only 2 in the book for it. But if you can just kind of, I think it was more important for y'all to practice right here with that rule where I broke up e to the negative 2k as something squared. So this is great, Stephen, taking it this far. Okay, let's go on to example 7.